Hello everyone, my name is Zhifang Li and I'm from East China Normal University. It is my pleasure to introduce our work at the PPLB conference. Our work introduces a new approach to fully expose CPUs and GPUs in data analytics. I will introduce the research background, motivation, design points, evaluation, and conclusion in turn. These features show that the computing power and memory bandwidth of mainstream GPU types since 2030. We observe that GPU hardware has developed rapidly in the past decades without the sign of stopping. This progress is beneficial to computing-intensive scenarios such as graphics processing, high-performance computing, and deep learning. However, a real system is based on the CPU-GPU architecture rather than GPU itself. This makes it complicated to apply GPU for data processing. For example, the PCI bus is still much smaller than the GPU memory, which is easy to become a bottleneck without the special optimizations. Besides, the size of GPU memory is also smaller than that of memory, which means we cannot assume that all data is in GPU. Therefore, how to explore GPU in data analytics is still an open issue. To figure out the current tendency to apply GPU in different fields, we search some keywords on Google Scholar. The result shows that there are significant field works to apply GPU in data analytics compared with graphic HPC and deep learning. This is almost similar for other modern accelerators, not limited to GPU. Our observations illustrate that applying GPU in data analytics is not a straightforward thing. Considering these facts, we need to couple with three fundamental challenges as follows. The first challenge is there is a long data path moving data to GPU. The standard Spark abstract partition data as RDD and computer RDD with JVM. When we add a GPU to computer RDD, it will involve extra GenI or RPC cores before data reach GPU through the PCIe bus. This process occupied 70% of execution time, as RDD should be converted into a GPU optimized format. The second challenge is that the current work are based on the case-by-case approach, and many consider each individual situation. Technically, this approach may lead to many to modify current systems or even build new systems. You can imagine that when there are n types of analytic systems and m types of device, it will lead to tedious engineering for so many combinations. More importantly, our implementations and optimizations are hard to reuse among different combinations. The last change is that the underlying optimization space of GPU is restricted by the upper analytic systems. Let us consider three typical situations as follows. First, GPU is stateless while GPU or CPU RDD data is stateless while GPU context is stateful, and the initialization of GPU context is costly. Second, the GPU processing model is role-oriented to optimize CPU execution, while GPU prefers a column-based approach. Finally, RDD scanning all consider homogeneous resource such as CPU or GPU, while a heterogeneous machine contains both CPU and GPU. This situation demonstrates that the current architecture makes it hard to apply GPU in data analytics. In order to solve all these challenges, our key idea is to decouple the end-to-end database into two parts. a data plane, and a control plane. This implementation allows the control plane and the data plane to employ different designs respectively. Based on this idea, we implement a framework called ShadowVM. ShadowVM leverages a lightweight control plane to adapt analytic systems and efficient data plane to directly utilize the CPU and GPUs without the restriction from the control plane. ShadowVM is inspired by two parallel technology that share similar points in different fields. For example, LLVM leverage diverse language handles uh, diverse language and architecture by using intermediate abstraction. Besides, user space IO leverage OS kernel as a control plane for authority management and provide a user library as a data plane that allows the user program to access NIC without trapping into the kernel space. Our design considers similar points in different in data analytics. In ShadowVM, the control plane hides the diversity of analytic system and the computing device, while the data plane opens the optimization space for CPU and GPUs. The design of ShadowVM has three core abstractions as shown in the right picture. First is leverage vrdd as the control plane, which is a virtual RDD that holds control information rather than real data. Then it leverages vkernel as the data plane, which is an execution unit that runs on a pod of bare metal CPUs and GPUs. The data plane can be deployed, detached, and long-lived process so that its context can be reused. Data can be directly loaded into the data plane in a GPU optimized format without the conversion. ShadowVM leverages action shadowing that offloads computing from vrdd to vkernel by changing the database. The right picture shows how to generate and execute vrdd. First of all, the user should write a program with ShadowVM's control plane API. ShadowVM will divide the computing actions into multiple pipelines based on their data dependency. And all actions in a pipeline can be executed without blocking. In order to reduce the number of pswitch and kernels to launch in the data plane, we generate a vrdd for each pipeline rather than each action. Since vrdd is still a normal RDD, it can be submitted to a standard spec without modifications. To deeply understand how the control plane works, we compare the implementations of RDD and vrdd. Let us consider a simple map as an example, which consumes a single RDD to generate another RDD. In the Java function of left picture, the normal RDD directly reads data from the iterator of previous RDD and then deliver computer values to the next RDD. However, as present in the right picture, a vrdd does not deliver any real data, but the lightweight barrel that notifies the termination of this vrdd. During this process, computing is offloaded via action shadowing, which sends the command of computer logic of a pipeline to the data plane. Let us consider a more complex situation such as motorway joins. This application consumes multiple vrdd to produce the final result. It is similar to the map but needs to wait multiple barrels from the previous vrdd with its data dependency. After the control plane offloads computing to the data plane, it will be executed as a vkernel. The data plan will generate both CPU and GPU code for each vkernel with two steps. First, the data plan built a blueprint for each target device and had the details of each action. Then the data plan filled each action with its implementations. After that, CPU and GPU code will be comparing to target objects such as SO and PTX files by using CLang and MCC compilers. Based on the target object, the vkernel will be launched and pthread for CPU and CUDA kernel for GPU. Local partition are assigned to CPU and GPU based on partitioned parallelism, and the vkernel sets the GPU-CPU ratio based on the runtime statistics and employ speculative execution to narrow the impact of scheduling error, which lead to struggles that delay the whole vkernel to return. Unlike deep learning and HPC, the PCIe transform is easy to become a bottleneck in data-intensive analysis. A traditional active copy will pull data to GPU memory as fast as possible. However, in data analysis, this strategy will restrict the workload size and the opportunity to reduce the PCIe transform. A well-known optimization of active copy is to overlap PCIe transform with computing. Technically, even with the perfect overlapping, the throughput of GPU execution cannot execute the bandwidth of GPU of PCIe bus. We observed that the vkernel processing data in a pipeline manner, which means we do not need to actually hold data in GPU memory. The data plan of ShadowVM employ passive prefetch that put all data in host memory and delay real transfer to vkernel runtime. This approach allows the GPU to skip unused data where there are multiple selective actions in a pipeline, such as filters and joins. Passive prefetch is integrated in code generation by using UVM pointers and skip condition for GPU thread. Because UVM initialization is costly, the decoupled data plan allows to reuse GPU context. This optimization is inflexible in traditional data panel design, which is restricted by the stateless RDD data. Unlike data Unlike deep learning and HPC, PCIe transform is easy to become a bottleneck in data-intensive analysis. A traditional active copy will put data to GPU memory as fast as possible. However, in data analysis, this strategy will restrict the workload size and the opportunity to reduce PCIe transform. A well-known optimization of active copy is to overlap PCIe transform with computing. Technically, even with perfect overlapping, the throughput of GPU execution cannot exceed the bandwidth of PCIe bus. We observe that the vkernels process data in a pipelined manner, which means we do not need to actually hold all data in GPU memory. The data plan of ShadowVM employs passive prefetch that puts data in host memory and deliver real transfer to vkernel runtime. This approach allows GPU to skip unused data when there are multiple selective actions in a pipeline, such as filters and joins. Passive prefetch is integrated in code generation by using UVM pointers and skip conditions for GPU thread. Because UVM initialization is costly, The decoupled data plane allows to reuse GPU memory context. This optimization is inflexible in traditional data plane design, which is restricted by the stateless RDD data. Next, we evaluate the performance of ShadowVM. We leverage both CPU node and the heterogeneous node with the extra GPU. Consider the price of GPU to make a fair comparisons. We use three GPU nodes for JVM-based Spark and one heterogeneous node for GPU-aware systems, including ShadowVM, OmniScience, and wrdd. The evaluate workload is to start a schema benchmark once all 13 analytic cycles on commercial data. The first experiment is carried out on the middle scale workload with a scale factor of 20 GB data. These pictures show the execution time of all cycles. ShadowVM outperformed JVM-based Spark by 6.4 times on the CPU-only model, 8.9 times on the GPU-only models, and 10.8 times on the mixed CPU-GPU model. ShadowVM outperforms GPU-centric amino science by up to 2.1 times by using both CPU and GPUs, while omniscience wastes the resource of CPU and do not reduce the pressure on PCIe bus. Rapidus is slightly faster than omniscience by using overlapping transform, but fails in some cycles. We observe that the cost of GPU context initialization is high in Rapidus as it does not leverage the decoupled data plane. The second experiment is carried out with a scale factor of 100 GB data, which clearly exceeds the capacity of GPU memory. By using passive prefetch, ShadowVM is allowed to handle this large-scale workloads once 40.7 times speed up. Uh, Due to the auto GPU memory issue, omniscience is switched to the CPU models, and Rapidus fails as it does not support a CPU-only model or mixed model. This to figure out how the data plane decoupling impacts the performance, we compare two different implementation of ShadowVM. One was the coupled data plane and another was the decoupled data plane. We compare the time distribution in the previous large-scale workload and show the results in the two pictures respectively. We observe that data plane decoupling avoids row-to-column data conversion and the initialization of GPU context that rejects the the memory space to the page table of OS kernel and the GPU driver. As a result, the data plane decoupling increased the GPU execution ratio from 18% to 85% by solving the two above issues. In the last experiment, we evaluate how passive preference impacts the performance in ShadowVM. Uh, these features compare the performance of active copy and passive copy for GPU execution. We use a classic overlapping optimization on the active copy version by increasing the concurrency of CUDA multi-streams. We observe that the permutation of overlapping is is still restricted by the upper bound of PCIe bandwidth due to the barrel effect when computing spend less time than data transfer. In contrast, passive prefetch breaks this restriction to save out to 80% of PCIe transform and achieve higher performance. Finally, let us we conclude our work. ShadowVM introduced a new approach to harness data analysis with modern computing device. We decouple the whole process as a lightweight control panel to adapt up analytic systems and allow computing to efficient data plan that directly utilize CPUs and GPUs without the restriction from the control plane. Currently, ShadowVM is available at GitHub, which include a Java-based control plane and a CUDA-based data plane. Uh, that's all. Thank you very much for listening.